Our third type of learning problem is reinforcement learning. Here, we're modeling an agent that's choosing sequences of actions in response to a changing environment. The agent receives feedback in terms of rewards and punishments, which are positive and negative points. However, this feedback is infrequent and delayed. This means the agent could undergo a long sequence of chosen actions before it receives any feedback about whether what it chose did it any good. Typical problems solved by reinforcement learning include playing games, robotic movement, and self-driving cars. The goal of the reinforcement learning model is to find a policy for choosing actions, which depends on context, that allows the agent to maximize total rewards over a fixed time period. The idea that the best action depends on context is consistent with our life situations. For example, whether to go for a run outside or in the gym depends on the weather. What we should eat for our next meal would depend on how hungry we were and what we already ate that day. In reinforcement learning, the context is the current state of the environment and can also include past states. The criteria that we want the agent to maximize total rewards means that it's not necessarily going to learn how to get to the most immediate reward. Instead, it's possible that the best actions will require the agent to undergo a long period of no rewards or even a string of local punishments before it gets the big reward at the end that made all the negatives along the way worthwhile. In this way, reinforcement learning can be used to model our struggles with self-control and delayed gratification. For example, when we're studying for an exam, we have to undergo a lot of painful study sessions before getting a good grade. Or we might have to forego eating a lot of delicious cookies in order to feel good in our body. In another parallel with human psychology, reinforcement learning models also incorporate the idea of time discounting. This means that rewards and punishments that are further away in time have less impact on an agent's choices. In real life, this is also the case with our human psychology. We're built to be influenced more by immediate rewards and punishments than delayed ones. We probably evolved to be this way because you can't ever be entirely sure about the future. You never really know what's going to happen. The world might come to an end, and then might as well have a cookie. One of the challenges in reinforcement learning is that this feedback is infrequent and delayed. This means that you would undergo a long sequence of choices before you get any feedback. Imagine you spend a whole day eating and drinking lots of different things, and it's only at the end of the day that you get an allergic reaction. It'd be hard to know exactly what you ate or what sequence of things that you ate that led to this reaction. With infrequent delayed feedback, it's hard to know what actions or what sequence of actions caused the reward or punishment. This is also known as the credit assignment problem in reinforcement learning. It's very hard to learn under these conditions, and this is why we need special reinforcement learning algorithms. Let's look at how we might set up a simple reinforcement learning problem with the example of a mouse in a maze. Here, the goal is that we want our agent, the mouse, to get to the cheese that will be worth 1,000 points. We want the mouse to be able to get to the cheese within 50 moves, no matter what its starting position in the maze. In our simple scenario, the only reward is the cheese, and in order to maximize rewards, this means we have to get the mouse to get to the cheese quickly enough from any starting location so that it hasn't taken more than 50 steps, which is when the time expires. We represent the state of our mouse with the configuration of the maze walls at the mouse's current location. We're going to assume that the mouse is myopic, so it can only see which of its 4 sides has walls versus not, and it can't see further along in the maze corridor. So if the mouse starts at the bottom left corner, then the starting state would be represented like this, with walls present on the left and the bottom, and no walls on the top and the right. We don't want the mouse to go through walls, so we're going to assign punishments in terms of negative points for hitting a wall. This means if the mouse were to choose to go left, it would hit a wall, it won't be allowed to go left, and it would get a punishment of negative 100 points. Similarly, if it chose to go down, it would also hit a wall, it won't be allowed to go down, and it'll get a punishment of negative 100 points. But if it chooses to go up, it will be allowed to go up. There isn't any reward or punishment, but it is allowed to move. If the mouse chooses to go right, again, it'll be allowed to go right, and there is no reward or punishment, at least not right now. Remember that the best chosen actions depends on the state. We can see for this state, which is there is a wall on the left and a wall on the bottom, but no wall on the top and the right. Choosing to go left is not good. Choosing to go down is not good because the mouse runs into walls. But so far it seems equally fine to choose to go right or to choose to go up. There are no rewards, but no punishments. Let's say the mouse moves to the right and ends up in this position. Here, the state, which is the local configuration of the maze walls, looks like this. A wall on the bottom, but there's no wall to the right or left or the top. Now, the mouse is able to choose to go left, and it's allowed to go left. If it chooses to go down, it will get a punishment, and it will not be allowed to go down. But it can choose to go right, it's allowed to go right, and it will be allowed to move with no punishment, and it can choose to go up, and it'll be allowed to go up with no reward or punishment. Here we can see that the best action depends on state, because the good actions to choose in this new state is different from the best actions to choose in the previous state, where there was a wall to the left and to the bottom. I'd like to point out here that in the reinforcement learning paradigm, the agent chooses an action, but the consequences for the chosen action is determined by the world dynamics. The dynamics of the maze world are such that when the mouse chooses to go down and there is a wall below it, the consequence is negative points and it stays in the same location. That is, it's not allowed to move. In general, in reinforcement learning, the consequences of chosen actions can also be probabilistic. So for example, if we were in a magic maze game, it could be that when a mouse chooses to take a step in a direction without a wall, 80% of the time it's allowed to take one step over in that direction as would be expected, but 20% of the time it might end up in a magic portal that teleports it to another part of the maze. Again, there's an analogy with the way life works, where we can do our best to prepare. For example, we might do our best to prepare for an exam, and this might increase the chances of doing well on the exam date. But despite our choosing our best actions to prepare for the exam, who knows what might happen? We could get sick, the school building could burn down, and the exam gets delayed. What we're doing in reinforcement learning is to learn a policy for choosing the best actions for each state that is most likely to lead to outcomes that bring us towards rewards. Let's go back to our non-magic maze. Let's watch the mouse go through this maze and see how the state changes as the mouse travels through. We're going to assume that by now the mouse has learned to avoid the walls. So imagine the mouse starts in the bottom left and the state of the world looks like this. The mouse chooses to go right. Now the state of the environment looks like this. The mouse can go left, up, or right, but it chooses to go up. This is now the new state of the environment. Now the mouse can go back down or to the right, and it chooses to go to the right. And the new state looks like this. With each action chosen, the mouse can end up in a new environmental state with new available choices. And only after choosing a huge long sequence of actions in response to each new environmental state does the mouse finally receive a reward. One of the main challenges of a reinforcement learning environment is that it's not clear which portion of the recent sequence of chosen actions led to the cheese. We are looking at a bird's eye view of the maze, so we see where the cheese is. But to the mouse, it just sees the local wall configuration. Let's imagine the mouse had just found the cheese for the sequence of chosen actions that we just saw. And now it's another round of the maze challenge. And let's imagine in this next round, the mouse finds itself starting here instead. We can see that the mouse is not in the bottom left corner, but to the mouse, the configuration of walls in its current starting state does look the same as it did when it was in the bottom left. Again, there's a wall to the left and a wall to the bottom. The mouse might think that it can just repeat the winning sequence that it had done before. Let's say the mouse tries to repeat the same sequence that it had used before. So it repeats its previous sequence of choices, and then it gets to a point where the sequence is broken because the state of the world is no longer the way it was the previous time. And if the mouse were to follow its previous choice, it would go up and it's going to run into a wall. A big challenge of reinforcement learning is to find which part of the sequence of past chosen actions and states were the ones that led to the reward. To add to this challenge, in general reinforcement learning paradigms, the rewards and punishments can be delayed. In our example with the cheese and maze, we have the intuition of a cheese located in a physical location in a maze, so the mouse will just get there when it does, if it gets there. But in more general reinforcement learning situations, the feedback can be delayed so that when the reward or punishment comes, it's not necessarily the consequence of the most recently chosen actions, but actually they're delayed consequences of actions chosen much longer ago. And this makes the learning problem even more difficult. Now you might wonder, is there a link between reinforcement learning and supervised learning? After all, there is a concept that's like a label, which is this concept of feedback in reinforcement learning. So why can't we treat this feedback signal as a label and treat all the possible sequences of states and actions that happened before getting this feedback as a single training example? And then gather lots and lots and lots of these examples of sequences of states and actions leading to a feedback, and then treat this whole thing as a supervised learning problem. The answer is, if there are only a limited number of states and actions, and it's easy to enumerate all of these that lead to rewards, then it is theoretically possible to transform a reinforcement learning scenario into a labeled dataset for supervised learning. However, in reality, the situations where we use reinforcement learning are the kind where there are so many combinations of states and actions that it's unfeasible to specify enough sequences and actions that lead to rewards, because the rewards are so infrequent. Often we might start a reinforcement learning algorithm with no idea of what choices to make to get to a reward, and the algorithm is learning to get rewards at the same time as it's gathering its own training data. Because the space of possible choices and states is so large and the feedback is so infrequent, we need special reinforcement learning algorithms that are strategically learning in real time how to update its policy for making choices in a way that maximizes chances of rewards. Otherwise, it's like trying to build a model that can win at a game of chess and hoping we can construct a data set of winning moves using random sequences of moves. It's like expecting a 4-year-old to beat a grand chess master through random chance. One of the major breakthroughs in deep learning was a deep neural network for reinforcement learning developed by the startup DeepMind that has since been acquired by Google. They implemented a model that could learn by itself to play many Atari games with human and superhuman level performance, without any human-led training. And what was remarkable is that this deep neural network had never seen the Atari games before and didn't know the rules to the games. The model used deep reinforcement learning to maximize its score given only the stream of pixels representing the game and the current game score as the input. DeepMind followed with another landmark achievement with a deep reinforcement learning model called AlphaGo, which was the first computer program to beat a human world champion at the ancient Chinese game of Go. This is the end of our lecture on supervised, unsupervised, and reinforcement learning, and also the end of our first module. You now have the background that you need to start learning about how neural networks compute and learn, which is what we'll be talking about in our coming modules.